Hello, my name is Zachary Chenoweth, and this is my presentation of Lab 4, Task 1, Mapping with Noise. So for this task, we have to have our robot start in a specified location and facing a specified direction, and we have to have it traverse the maze, mapping all the internal walls with noise to all the sensors. So the distance sensors, the IMU, the position sensors, etc., all have about 10% noise. So first off, we have all of our initializations of the robot. This is the same depending on whatever sensors you're using. So it initializes the camera, the distance sensors, the position sensors, etc. Here's where we have our specified direction and position. So direction is north, south, east, and west based off of whatever direction we're facing, and it's just the first letter indicating north, south, east, or west, respectively. The position is the current starting position of the robot. So in this case, it's at cell 16. So it's at coordinates 15, negative 15. Cell 16 at 180-degree angle, which is what north is. And then this is for an initialization of our movement, which we will use later. Here I have a data structure for the mapping of the maze. It starts off blank, so none of the internal walls are mapped. All that it's mapped is the external walls. Here we have our print function. So all of this does is print this maze and shows which cells have been visited and so on, and as well as the walls and stuff once we map them. This mapping function is what actually maps the walls. This is the same as it was in my previous video with the non-noise solution. So we have, depending on the direction, if the distance sensors are reading a value less than 10, then there is a wall there. So go ahead and go into this grid cell function. And go ahead and mark the appropriate wall depending on the direction. So for example, the front distance sensor, if our direction is north, the front distance sensor is the north wall. The left distance sensor is the west wall, and the right distance sensor is the east wall. And this changes depending on the direction we're facing. So like, for example, south, the front would actually be the the south wall would be the front distance sensor, the left wall would be east, and the right would be west, and so on and so forth. And then once the walls have been mapped, we're going to go ahead and update that grid and return it. Print information just prints all the required information, such as the robot pose, the distance from the walls detected based on their absolute orientation, as well as the grid with the visited cells and the internal walls. Update pose basically just updates the position of the robot as it's moving along. So it updates the X and Y coordinates based on the distance traveled. It updates the angle, the actual angle, and then it updates the cell number, again, based off of the direction it's currently facing. This function is what moves our robot forward. All it does is it uses the position sensor to read if the robot has traveled at least 10 inches. So if it hasn't traveled 10 inches yet, then it's going to go ahead and set the motors to 6.28 radians per second, which is the max speed of the robot. And then once it's finally hit 10 or greater, then it's going to go ahead and stop the robot and return whatever the distance traveled was. This turn left function basically only turns the robot 90 degrees to the left by calculating the velocity using kinematics formulas. We're going to go ahead and calculate the velocity it takes to turn 90 degrees in 1 second, and then set that velocity to the wheels so it'll turn 90 degrees in 1 second. Now, because we're doing it based off of time rather than using the IMU, because the IMU has noise, when it turns, it might be slightly off by like a degree or two, but nothing super significant. And then once it's done turning, then it's going to stop the robot and then update its direction it's facing, and then return that direction. Same thing for turning right. It's going to do the same thing. It's going to calculate how quickly it needs to turn 90 degrees in 1 second, set the velocities. Once it's finished turning or once time has passed, it's going to stop the robot, update the direction. Here we have the move function. This basically will tell the robot what moves to make based off of priority of the cells. So the way that my functions work is that if we call the turn left or turn right function, all the robot will do is turn 90 degrees. It does not move forward yet. So all it does is make that turn. And the reason I did that is just because when we're in this corner here, I thought it would be easier just to turn so that way, and it doesn't try to move forward to run into the wall. So if our last motion was a left or a right turn, then we want to prioritize the forward motion first. So as long as there's no wall in front of it, then it's going to go ahead and move forward. Otherwise, it's going to make another left turn if there's no left wall, or a right turn if there's no right wall. So the priority is for if the previous motion was a left or right turn again, is forward, left, then right. And then if none of these apply, we go ahead and turn left. And this is just in case that there's for some reason it's surrounded by walls or the robot thinks it's surrounded by walls, it'll keep turning. If the previous motion wasn't a left or right turn, then the priority is based off of visited cells first, or non-visited cells first, apologize. So basically, depending on the direction that the robot's currently facing, it's going to go into these if statements for north, south, east, and west. And then it's going to check if the left distance sensor is reading a value and if the cell that it's trying to go to has been visited already, then forward, and then right. And then if all the cells around it have been visited already, then it's just going to prioritize left motions, then forward motions, then right motions first. And then if all of these fail, then it's going to go ahead and turn left. So once again, the priority is left, forward, and right non-visited cells first, and then left, forward, and right visited cells. And then it does that for each of the cardinal directions. And then once it's done doing the actual motion, we go ahead and update the pose of the robot by calling that update pose function I showed you earlier. And then we're going to go ahead and return the direction, the pose, and the motion. The check done function, all it does is it checks when all the cells have been visited in the maze. And that will tell our robot that it's done mapping and it can go ahead and stop. These function calls here are to make the robot turn in its starting place, because we will find that in some examples, like for example, in cell 10 here, if it does not turn back and then turn in its original direction, mapping this wall here, this wall won't get mapped from cell 10. It will get mapped from this side, but when you look at the maze or the grid when it prints, it'll show that it sees a wall missing here, which we can't have. So to fix that, we at the very start, we turn left to map this back wall and then turn back into our original position. And then this is the main loop, which just basically keeps looping through until check done becomes 0, meaning that it's all the cells have been visited. So now that's the code. Let's go ahead and see it run. Go up here. So once again, we're starting in cell 16. So let's go ahead and start it. You can see it turns and then turns back before beginning its motions. As you can see, it's going through, it's updating the position of the robot. It's showing the distance between the walls that it's reading, and then it's showing the walls that it's detecting based on its absolute orientation at the time, as well as updates this map so you can see the V represents the visited cells as it's going through, and then as it's mapping, you can see the zeros are becoming ones, meaning that it's detecting a wall there. So it'll keep moving through. And now it's going to go ahead and turn left here. And it's just going to keep going until it has visited all the cells and all the walls have been mapped. And then once it gets to that cell, it's going to finish. Now we can go ahead and check and see if all the walls have been mapped. So we see two walls here, here and here. We see the one wall hanging down here. We see the one wall up in the corner here. And then we see this kind of U shape of walls here. So here and here, which represents this. So all the internal walls have been mapped. Let's go ahead and see one more example. Let's go ahead and put it in cell 7. And let's go ahead and face it west. We're in cell 7, and we're going to go ahead and face west. So this is the starting position, and then at cell 7, the coordinates are 5 and 5. Let's go ahead and update that. And then since we're facing west, the angle is negative 90 degrees to start with. Now that that's done, let's go ahead and run it. So it does that turning motion to check if there's a wall behind it, and then it's just going to run through the maze like normal. I'm going to go ahead and speed this up because it's the same thing as before. And then once we're done, we'll go ahead and check the maze to make sure that it mapped all the walls. So again, we have the two walls here, the walls here and here, and then this U shape of walls here. So all the internal walls have been mapped and our program is complete. That was my presentation for Lab 4, Task 1, Mapping with Noise. Once again, my name is Zachary Chenoweth, and I hope you have a wonderful day.